Okay, welcome everybody. Good morning, afternoon, or evening, depending upon where you are listening from. Welcome to the NASA Earth Data webinar, NASA's Soil Moisture Active Passive Mission, or SMAP Data Products webinar. This is your host, Jennifer Brennan. While everybody is logging in, we'd appreciate your feedback on the two optional polls at the bottom and middle portion of the page. I do have 2 p.m. Eastern Time, so we're going to go ahead and get started. First, we'll begin by going over a few housekeeping items related to the webinar. To ensure best audio experience, the conference has been placed in silent mode. For those of you who have unmuted yourselves, please be sure to keep your phone lines muted. We are recording this webinar. If you have any issues or any questions, I would like for you to enter them into the Q&A pod located on the lower right-hand corner of your screen. This works like a chat. The webinar, as I said, will be recorded and posted to our NASA Earth Online Adobe Connect event catalog, as well as to our NASA Earth Data YouTube channel within a few days of completion. These URLs will be provided to all of you at the end. All presentation files will also be available for download at the end of the webinar. Regarding the timing, the webinar itself is 1 hour long. 45 minutes are allocated to the presentation, with another 15 minutes for the questions and answer period. After the speaker has finished his presentation, we will then move to the final set of polling questions. As I mentioned earlier, you will have an opportunity to ask your questions throughout by using the Q&A pod. However, questions will not be answered using the raising hand function. It has been disabled. We will take all questions using the Q&A pod at the end. So let's move next to the agenda. I'll pull that up here. During the first 5 minutes or so, our speaker will provide you with an overview of the NASA SMAP mission. The next 10 minutes will focus on the standard design for all SMAP data products, followed by an overview of SMAP data products including product names, resolution, granule coverage, product sizes, initial delivery dates, and latencies. And then finally, we will finish with a basic description for all 15 of the SMAP products. With that, it is my pleasure to speaker today, Barry Weiss, who is the SMAP data architect at the NASA Jet Propulsion Laboratory. Barry?
Good day to all of you. As I see, people seem to be coming in from lots of different places, so I'm not going to guess what time of day it is. I'm quite enthusiastic to present to you the data products that are going to be generated by the Soil Moisture Active Passive Mission, or SMAP. I want to quite enthusiastically say to you that SMAP is now flying, and we have been generating data for about the last 30 to 45 days. The data right now are in a mode where we are calibrating and validating them, and therefore they aren't yet available to the public, but the data are quite good already, and we're very pleased with where we're going. So without any further ado, let's get started in terms of what we are doing and what we're going to discuss today. So first of all, again, my name and my institution. I'm a proud member of the Jet Propulsion Laboratory at the California Institute of Technology in Pasadena, California. And by the way, surprisingly enough, it's been drizzling this morning. I know most of you think, well, Southern California, well, yeah, we still don't have nearly enough moisture here. So, as Jennifer mentioned, the basic outline of the discussion is in front of you now. I will give you a quick overview of the mission. I'm going to talk about standard design of the products so that those of you who are not familiar with them can pretty quickly get into the products and use them. I'll list the products, provide a description of each product, and then provide you with some contact or additional information about the products. Okay. I doubt, looking at the list of people and what you do, that I have to convince you in any way, shape, or form why soil moisture matters. I think you already know. But one thing I do want to point out is this particular plot, and I do believe it's radar data, indicates already the operational nature of our instruments. We are already taking data. They are looking reasonably good. Yes, there are features that some of you would look at and say, what's that? Well, those are items that we do need to remove. For instance, you can see sort of swath patterns over the ocean. Well, that's not appropriate. Those are the kinds of things we will be working on over the next couple of months before we deliver the products to you. Okay, so down here, again, why it matters. I, again, don't think I really need to point these out in detail, But I think most of you are aware that soil moisture can be used for any of these particular applications as well as others. So onward with that, we'll go to a little bit of information about the mission. What is special about SMAP? Well, I think many of you who are familiar with remote sensing probably know that L-band radiometers, or radiometers of that particular frequency range, have proven to be good instruments to measure remote sensing, to measure soil moisture in a remote sensing mode. The problem with those radiometers is the resolution. The SMAP radiometer will record data at about a 40-kilometer resolution, meaning it's not a really fine resolution in terms of what you might want to do with the soil moisture information you gather. The magic or the special part of SMAP is combining that radiometer with a radar measuring at the same locations. The radar is a synthetic aperture radar with a 1-kilometer resolution. Now, radar does not have a strong history of use for soil moisture measurements, but we will use it with the radiometer to provide the kind of resolution you're interested in. I want to point out one other point here, which is the radar will also be used for freeze-thaw state detection. The radar will also be used for standing water to determine where there might be water under situations where we would not expect them by looking at a regular global map. So for instance, if there are pools of water in one place or another, we know how those would impact the ultimate measurement. Now, one quick point in terms of what SMAP is doing. Again, the radiometer, we know, is an effective measure of soil moisture. We're going to look at the footprints or the measurements of the radiometer, and we're going to subdivide them based on the variation of radar measure within the radiometer measure. Again, we're going to look at the variation of radar measurements within a single radiometer measure, and then subdivide or disaggregate those radiometer measurements, and then use those to retrieve soil moisture at a finer resolution. That is the really specific, shall we say, application of SMAP that will provide people with a much finer resolution of soil moisture than has been provided before using remote sensing equipment. The two instruments share a common antenna. It's a rotating antenna, and it is 6-meter diameter. It rotates at approximately it rotates at almost exactly 14.6 RPM, so about once every 4 seconds, a complete rotation of the antenna occurs. We take data at an incidence angle of around 40 degrees, and very importantly, having this rotating antenna enables us to take data at about a 1,000-kilometer swath. With that width of a swath, we're able to take data over the entire Earth or have global coverage of the Earth once every 3 days. Now, the orbit is sun-synchronous, and it repeats every 8 days. However, about every 3 days, we do get a view of the entire Earth. I will talk about half-orbits in a moment. The half-orbits are divided into two. The descending half-orbits are those where we're going from a northern position to a southern position, and they are acquired at approximately 6 a.m. local sun time. The ascending ones, going from south to north, acquire data at approximately 6 p.m. local time or sun time. The plan of the mission is approximately 3 years baseline, or not approximately, it is. Forgive me for using the word approximately too many times. On to the next slide. I'm going to now talk a little bit about the product definition and how the products are designed, because they all are designed commonly and pretty much with the same design. I'm responsible for this, so I think I can talk to this quite clearly. As we worked with the data products, I tried to make sure that all of the products clearly conform to mission requirements, but also they have a consistent format and architecture, which I'll talk about. Also, they contain self-descriptive information. I'm hoping that those of you who use these products don't have to go and look at reference documents all of the time, but rather can find a lot of the self-description information in the product, and therefore, they are easy to use. Okay, so what did I do, or what did we do? I led this effort in terms of design of the products, but there are an awful lot of people who have designed and worked on these products and generated what I think will be fine data that you can use in your investigations. First of all, I'll talk about product types or collections. When I talk about a collection, I'm talking about a series or a set of data. And what we're saying is when we see the 15 different products, each one of those would be a single collection of data. And I'm going to say that all of those products, regardless of which collection they all conform to a standard format. I may use the word granule or file occasionally. That's each member of each collection. So each individual granule or each individual file is one instance of each product. Now, when I talk about the products, I'm going to talk about algorithmic output and I'm going to talk about ancillary data as well. Both of them are going to be in the products. The most important algorithmic output that most of you will be interested in by looking at the screen before is the soil moisture. However, we will provide ancillary data that will help you better understand the soil moisture. Most importantly that I want to emphasize is the data products are going to be in HDF5. Now, at the end of this presentation, I have additional materials that can define will provide you with more information than I can possibly cover in a 45-minute span. There will be 2 slides in the backup that describe how you can use either MATLAB or IDL to read HDF5 easily and quickly. I also at the end will indicate a reference to HDF so that if you have some other software method that you're going to use to read these products, you can get information on HDF to better be able to prepare you to read the products. What I've done is I've used the grouping mechanism in HDF, which I think is very powerful, to group the data. And the groups contain data that are conceptually related. Within each group, I make sure that the dimensions of the elements in the product, which we call data sets, all have the same shape. Therefore, they're easily interreferenceable. And I also make sure that when we use the indices, you'll be able to tell which elements actually match up with which elements. And the next slide will make that more clear. I'll also talk just a little bit about metadata very briefly, but what's important about metadata is these are data that describe data. This is how you will get self-descriptive information out of the product to be able to do what you need to do. There'll be 2 categories of it: product metadata that describes an entire file or entire granule, and local metadata that describes each of the individual data sets in the file. So for instance, one data set in many of the files will be named soil moisture. I think you know what that contains. There will be local metadata that gives you information about that particular array that will provide you with more information. Okay, so here we have a model swath. Envision this is the radar level 1 swath. I'm pointing out a little area in here where we have data, and I'm then pulling out what looks like a grid, which would be correct. The level 1 product has a grid that conforms or aligns with the swath. Then I'm pulling out a particular pixel. And in that pixel, we have all of these different data arrays, a latitude, a longitude, and sigma knots, which are radar measurements. They are radar cross-sections, normalized radar cross-sections, for both forward-looking and aft-looking and the HH and VV channels. And we're saying that all of these have indices HM, or shall we say an ordered pair of indices NM. If the ordered pair or the indices match up, then these elements reference the same pixel. That's a very important point. All of the elements in a group will have the same dimensionality, and then if they have matching indices in that group, you know that they reference the same data pixel. And this is a pattern you will see in all SMAP products across the board. So the next slide. This again sort of details what I mentioned a moment ago. The level 1B radar product has 3 major groups in it. These groups are all conceptually aligned. These groups have a shape. This group and this group are one-dimensional. This group is two-dimensional. Notice that when I give you examples of elements in the group, I say to you, if they have the same index, they reference the same pixel. I further indicate that maybe there's some kind of a particular element that they all align to. So in this particular group, they all align to a time value. So this time value with this particular index contains the time, when these two measurements were acquired. Again, this particular time is the time when these two measurements were acquired. Here we have a two-dimensional array, so these two match up with each other. This time, however, gives us the time for both of them. This indicates an additional element in that particular product. In this case, it's the slices of the sigma naughts, which I will explain in a few moments. All right. Product metadata. This I will not go into in great detail. I can take a lot of time on this, and it's not what this particular topic is about. Again, however, product metadata provides an awful lot of information about the entire product. And as I look down here quickly, and you will look as you follow me here, I think you'll see that a lot of this information may be of interest to you about the mission, about the space and time of the data, about the algorithm used to calculate the data, about various versions that were used. Lineage, this is really important information. This is what input was provided to get the output, both in terms of the algorithm that was used and in terms of the data that were used. Orbit mechanical information, instrument information, other tables that might tell you something about calibration. All of this is in the product metadata. Some of this may be of value to you. You should be aware it's there. Local metadata, as I said a moment ago, provides information about each array. So if I have a particular array, again, soil moisture, that local metadata, which is in what we call attributes attached to that particular array in HDF, will give you a sense of what the minimum value, the maximum value, the units, the dimensions, all of those things will be defined in each local metadata element attached to each array in HDF attributes. All of them are there, and indeed, I encourage you to get familiar with this, because if you do, you will have self-descriptive information that will help you better understand the products that you're looking at. The global metadata is ISO 19115. All I'm going to say about that, you can read the rest, is this is a relatively new international standard of metadata. The concept here is, in the past, different people have used different metadata standards to represent their products, and then what happens is when you go to different products, different names or different elements describe the same thing. The whole point of using a common international standard is everybody will use the same names and the same groups to define the same elements. It also requires that we represent them in a common way. So both a common representation and a common model enable people to use products across the board internationally. SMAP is the first NASA mission to use ISO 19115. On the local metadata front, what I want to point out is the names of the local metadata, the maximum, the minimum, the fill value, are names that conform to this convention. Those of you who know NetCDF probably will be very pleased with that, because this convention is used strongly with NetCDF. By the way, one of the other things we've worked on is to try to make sure that people who are familiar with NetCDF can read our HDF products in NetCDF. So the maximum value of a particular array is called valid_max, because the CF convention uses that term. The minimum value is called valid_min. Again, the CF convention requires that. So for those of you who have some familiarity with products, I'm trying to point out that we're trying to conform to what other Earth data science providers are also doing. All right. I think this chart will sort of sum it all up, and then we can move on to talk about the data products themselves. This large area represents an entire data product. This particular pink area represents a particular group, a single group, that contains the product metadata. This is the ISO 19115 metadata that describes the entire product. But the metadata are in here. We use HDF to store the data in a particular form that will be easy to read. We also provide the data in the XML form that the ISO standard requires. If you are interested in more on HDF metadata or ISO metadata and how I provide it, I have done another seminar on that. I can provide that information to you. Here is an example of a single HDF group. All of these data in this group are conceptually related. They also have the same shape. Therefore, if you look at this particular array and this particular array, you want to know two elements that represent the same pixel, you look for a common set of indices and you have it matched up. Each of these arrays also have local metadata that describe the content of that particular array. So maximum, minimum units, etc. for this array is in local metadata in attributes attached to this array. The same set is in this array attached here so that you can identify them because of how they are placed in the product. Finally, there can be more than one group. This group is also conceptually related, perhaps conceptually related to that, perhaps not, and interrelated, and the documentation will indicate that by dimension sizes and dimension definitions. We will indicate that way whether the dimensions here match up with the dimensions here. Again, it's all in the metadata. All right, finally, many of our products from level 1C radiometer through level 2, level 3, and level 4 all use the EASE grid. The EASE grid is an equal area scalable grid developed for the SSMI project and sponsored originally by the National Science and Ice Data Center in Boulder. This particular grid is used for all of our products at the higher level. It is a static grid. And what we use are grids at either 3 kilometer, 9 kilometer, and 36 kilometer resolution. And the grids are nested so that if we have a 9 kilometer grid, when we have the 9 kilometer grid, you can actually say that 16 9 kilometer cells fit perfectly into one 36 kilometer cell. Therefore, when you look at our products that are 3 kilometer, 9 kilometer, and 36 kilometer resolution, you can fit the cells of a finer resolution into a larger cell of the broader resolution, and you can use that reference to do so. So as we move forward, I'm going to mention this, and also at the end, I will provide you with a reference so you can learn more about the EASE grid if you need that information. All right, the data products. I have a hunch this is where we all wanted to be. The next three slides list the data products. On the far left, over here, I'm listing the short names of the data products that we use. These short names appear in the file names. Again, at the end of the presentation in backup, I will provide you with file naming conventions. We'll not have time to do it in the talk, but they are there. So if you pick this up, you will have the file naming convention, and you will see that this character string appears in the file names identifying which file type you have. Here's a short description of each file. Here's the grid resolution of each file, and this indicates the granule extent. Please note that all of these are in the half-orbit form. In other words, as I mentioned earlier, we divide the orbit into halves, an ascending and a descending half, and each of the products are defined by which half-orbit you have, as well as which particular product you're using. Note, however, when we get down here, these products are all global. They are global maps providing global information, and this one single product, the freeze-thaw product, contains data north of 45 degrees north. You will have a polar view of the data from 45 degrees north up towards the pole. And onward. So the next particular piece here, again, the short names, again, the description. Here we indicate when you will first be able to see the data. The first distributions will be beta product distributions, meaning that we don't necessarily guarantee at this point that the data will be entirely validated, but they will be as best quality, obviously, as we can make them. And you'll notice that these products will be available on August 1st. The rest will be available November 1st. This column indicates when we intend to put out our first set of validated data products, ones that we've actually validated against ground truth. And again, these products will come out November 1, and these products will appear next year in the validated form. Hoping most of you will actually begin to look at the products here, even though we will produce better ones at this particular juncture. And also note, we will continue to work to improve the products over time. We will not stop trying to improve upon our products on May 1, 2016. It will persist as long as the mission is alive. Finally, note the latency here. This is the time it takes from when we acquire the data to when the data should appear at the data archive where you can pick the data up. These products will appear in about 12 hours, these in about 24, these in about 50, and notice these two last products, these are modeling products. They will take 7 to 14 days before they appear at the distribution archive. One other important point, these are averages. Some of these products may show up later or earlier. It depends on how long it takes to process the data and get them out to you. Okay, again, the list with data volumes. Now, this is where I mentioned a moment ago, if I didn't, I'll mention it now. There are still some things that are under flux. There are some things that are still changing. And since they're changing, these volumes may not really entirely hold. But what will hold is they will give you a good order of magnitude, or even better than that, measure of how much volume you need to store these products if you're interested in them. So indeed, if you're interested in collecting the data over a long period of time, the yearly volume will be of interest to you. And you'll see that there really are only 3 products, the 2 level 1A products and the level 1C radar, that really require a large number of terabytes in order to store. Most of the others require only a small number of terabytes or even fractions of terabytes in order to store over a year. So this is information you can use as you prepare to use SMAP data to make sure that you have an adequate amount of resource available to keep those data online for as long as you need them. Okay, now here we go. There are 15 slides ahead, and with each of them, I am going to do my best to try to describe each of the data products that SMAP is generating. This is the level 1A radar product. The level 1A products contain parsed telemetry. So what we're doing is we're taking the telemetry downloaded from the spacecraft and we're putting it into individual elements, and then each of those elements by name will indicate what the content is. What's important here again to notice is the product is divided into groups. And as I indicated to you before, each group contains data that has a common reference or a common conceptual content. Also, each group contains a common shape. Spacecraft data group. This is you're going to hear about with all the level 1 products. This contains the spacecraft position, the spacecraft attitude, also the altitude, other information about the spacecraft. The frequency that it appears will vary from product to product. Notice in the level 1A, it's every 1/10 of a second. The revolution data group. We're talking here about that rotating antenna. So for each rotation, we have some representative information. The representative here, information here about each antenna scanner rotation are things like the length of each pulse repetition interval or segments. Segments are divisions of the rotation into 16 individual segments. So information at that level is here. High resolution and low resolution. I mentioned a moment ago that the radar is a synthetic aperture radar. However, we take the data both in synthetic aperture radar form and we actually convert it, or on board, into what would be real aperture radar form. The low resolution data group contains real aperture radar. The high resolution data group contains the synthetic aperture radar. Note that I mentioned that these data are in block floating point quantizer format. If any of you choose to use that, we can provide the documentation about how to convert that into usable data. These data and all of the others are standard IEEE formatted data that you could read directly off of the file. The loopback trap data, these are data that we transmit, run through a filter, and then receive on board. This gives us some sense of being able to track instrument drift and calibration information. Finally, health and status data. These are things like voltages and temperatures that give us some sense of of the behavior or of the characteristics on board in terms of temperatures, voltages, other things as we're moving forward. Note that we convert these from data numbers to engineering units as we move forward, as we move through the product. So each of these has those measurements for each individual half orbit. Okay, the level 1B data. The level 1B, both for radar and radiometer, contain measurements. They are individual field of view measurements of the instruments, and they are in time order. So we're taking each brightness temperature measurement that we have, or no, excuse me, this is radar. So these are radar cross sections. These are normalized radar cross section measurements, and we are putting them in time order. Notice the coverage is continuous. We provide it over the entire data set. By the way, this is real data that has come recently off of the SMAP instrument. The data are Earth located. We geolocate them. We provide the radar backscatter both for copole and crosspole measurements. So both horizontal polarization and vertical polarization transmitted and received, both copole and H-pole. The KP measurements here, these are measurements of error. KP is a standard deviation. It's the normalized standard deviation of the sigma naught measurement, or of the radar cross-section measurement. Again, I mentioned this before, the orbit and attitude information are available. We have short-term and external calibration information that we provide. And finally, we provide slices of these measurements. So we have the whole footprint that we provide, but then we divide the footprint into individual 5-kilometer footprint slices that give you better resolution in this level 1B product. The level 1C radar product. This is the SAR product. We get 1 kilometer resolution on this particular product. The product is restricted to land and coastal water right now. The resolution can vary actually from around 400 meters to 1.2 kilometers. In the area on the edges of the swath. In the mid-swath, however, the resolution can get quite severely bad, at the order of 150 kilometers. I'll mention more about that in a moment. The nadir looks, therefore, by the way, are thin slices, and therefore, you can sort of see it here. They look fuzzy. They don't look quite as good as the measurements on either end. Okay, so these again are measurements of H-pole, V-pole, and cross-pole. However, they are now put into a 1 kilometer swath that follows the orbit swath of the spacecraft. As I indicated a moment ago, the resolution is good in much of the swath, but in the center of the swath, it's not good. Around 70% of the swath provides good resolution. We divide the data by forward and aft looks. We provide the spacecraft data. This also contains short-term and external calibration information, and we reference the EASE grid here. This isn't in the EASE grid, but we tell you where each of these particular elements fall within the EASE grid. The radiometer product. This is going to look highly analogous to the radar product, the level 1A. Again, it's parsed telemetry. The spacecraft data is the same kind of spacecraft group that you see in the radar. However, this one appears once every antenna scan, about once every 4 seconds. There's subband and full band moments data. These are the telemetry subdivided up. Couple of important points. 5 radiometric states. Antenna. That's the state that you're interested in. That's the state where the data are being acquired. These other states here with external noise diodes, internal noise diodes, are used for calibration. What's the difference? Well, I mentioned a moment ago that the radiometer takes data at 1.4 gigahertz. We divide that radiometer data into 16 subbands. Each of those subbands are one of the methods we use to determine when we have radio frequency interference. So in a moment, I will come back to this where we talk about radio frequency interference and a little bit more about what the radiometer product does to do that. Detail again on that would be in documentation, something I will not cover here. All right, so both of these contain V-pole and H-pole. They contain moments, 4 different moments, which are the individual pieces of measurement. And note that these appear once every 4 PRIs. This is once every PRI. 48 of these PRIs make one full footprint of the radiometer data. The housekeeping data group is highly analogous to the one on the radar, where we provide voltages and temperatures, and we convert them into measurements that you can view. The level 1B, the level 1B radiometer product, like the level 1B radar product, these are time-ordered field of view values, but here they are the brightness temperatures. Note that the resolution, 39 kilometers by 47 kilometer ellipses. Note that we provide brightness temperatures and antenna temperatures. Antenna temperatures at the antenna, top of ionosphere temperatures. What's not listed here, we also have top of atmosphere temperatures below the ionosphere, as well as surface reference brightness temperatures. We take data on all surface types, and we provide all 4 Stokes parameters, noting that the 3rd Stokes is used for Faraday rotation corrections, which is an important feature that we need to use to make sure that we have good polarization measurements in terms of what the true horizontal and vertical polarization measures are. As I mentioned a moment ago, we look at time variation, frequency variation, and polarization diversity to determine whether or not RFI is detected. We do determine whether or not we see radio frequency interference and where. We separate the forward and aft looks, and we can include spacecraft information. The level 1C radiometer. This contains the level 1B radiometer data, but now they have been categorized or moved into the EASE grid, a 36-kilometer EASE grid. So now basically we have resampled the data into that grid. We represent the grid in 3 different forms, a global cylindrical grid, a north polar grid, and a south polar grid. We separate the forward and aft looking data. What's most important about this is the higher level products that use radiometer data use this particular product as their referential or starting product. Okay, soil moisture. We have 3 soil moisture products, one based entirely on radiometer, the one that's in front of you now, one based on radar, and one based on both. Okay, these products appear, this product, the radiometer product, appears in the 36-kilometer EASE grid cell. Please note, this is represented in a one-dimensional array. Okay, so we have one dimension that represents each EASE grid cell that is in the product. This has foiled some early users of the product. Please remember this when you're looking at it. It is not two-dimensional. When I get to the level 3, they are two-dimensional. This, by the way, is a means by which we save space. We only list those EASE grid cells that really are associated with the half-orbit swath. We avoid the others. Notice this is the basic requirement on the data, that we will provide soil moisture over land with 4% accuracy, provided we have a low or moderately vegetated area. We define vegetation using the vegetation water content, that it's less than this particular threshold. Provided it's less than 5 kilometers per square meter, we consider that to be low or moderately vegetated. We apply water body corrections in freeze-thaw. As I mentioned earlier, this comes from the radar. And we also provide soil moisture estimates. These soil moisture estimates are based on AM observations. This could change at some point. We could provide PM, but right now the requirement is only AM. Note also that we have quality masks that indicate urban areas, mountainous terrain, dense vegetation, precipitation, snow and ice. For some of these, they will inhibit the capability to retrieve soil moisture, but for most of them, actually, we still will retrieve the soil moisture, but we will indicate these conditions because that indicates that perhaps the soil moisture retrieval was not at the level we might have wanted, or might have expected, or might not meet quite the accuracy that we anticipate here. But for instance, I know that for urban areas right now, we are not retrieving soil moisture. All right, high resolution. This is based on radar. A moment ago, I mentioned to you that the radiometer has a history of retrieving good soil moisture by remote sensing. Radar, not so much so. This currently is an experimental product that we hope to make better over time. Few things. 3-kilometer cylindrical cells on a cylindrical grid, not 36, much finer. Why? Well, the radar has much better resolution. Again, the one-dimensional array. Again, it's only on the half orbit that we use. Note here, the AM product is the entire landmass. We also have a PM product north of 45 north. Why? We're using this for freeze-thaw, where we want both AM and PM data. Okay, so we also employ, again, I mentioned this before, we use a 1-kilometer high-resolution level 1C, the SAR data, to generate these. We put them into a 3-kilometer cell. This reduces noise, makes the data less noisy, more reliable. The soil moisture retrievals can be done based on snapshot or on time series. And again, as I mentioned before, depending on terrain, we can have multiple models of this. No, I haven't mentioned this before. This is something about the terrain. We actually differentiate between terrain on these things. We have data cubes that will determine what the value might be based on what we think the terrain is on the Earth, particular crops, particular plant types, things like that. The freeze-thaw and transient water body are what we produce out of this and use it. And again, this, like the other product, contains quality masks about urban areas, mountain areas, and such. The active-passive product is the prize. It is the one that combines the radar and the radiometer into a 9-kilometer grid. It is, again, the one-dimensional grid. Again, we only see the data, we only see cells that are in that swath. I want to point out this mid-swath area. This is the area where we're saying the radar has bad resolution. In the original plan, we were not going to provide these data. We may very well provide them with a marker indicating that it is mid-swath and therefore may not provide the resolution at the level that we were hoping to provide or that we can provide. Again, notice that this merges the radar and radiometer channels using a time series algorithm. There is a time series algorithm and spatial heterogeneity that are used in order to combine the data and come up with the final product. I mentioned the disaggregation earlier, the disaggregation from 36-kilometer into 9-kilometer resolution using the radar to subdivide the radiometer measurements. This I've mentioned before. It's the same product again in terms of the low to moderately vegetated areas. The water body and freeze-thaw data come from the radar, and again, we mask for the same kinds of information here. Now, I see I'm moving a little slowly, so I'm going to move a little swiftly through the level 3 products. The level 3 products contain the same data as the level 2 products, however, they are global. So the radiometer level 3 product is a combination of all of the level 3 data on the same UTC day. The way we do this is all of the products that match on that particular day are in this product. All of the other specs are the same. The most important thing to note about this particular product and the other two is this. In the high latitudes, some of these swaths that we have here will overlap. When they overlap, we will select the value that is closest to 6 a.m. local solar time and post that one in the product instead of posting multiple values. Outside of that, this is, again, a joint set of all of the level 2 products for the same UTC day for the radiometer measurement. The radar, again, it's the same piece again, all over again. All of the measurements from a single UTC day, all joined together in one single product where, again, most importantly, in the high latitudes, we pick the value that is closest to 6 a.m. local solar time. And one last time with the level 3 active passive, again, we do the same thing once again. But this, of course, is the prize product. This is the one that will provide the 9-kilometer resolution based on the radiometer algorithm that we've proven before. Let me put it that way. It's based on the radiometer algorithm that we've used before at 9-kilometer resolution, a better resolution than has been provided in any previous attempts to measure soil moisture using remote sensing equipment. Okay, 3 more products here. The freeze-thaw product provides freeze-thaw over the boreal regions. We measure both AM and PM measurements. The reason we measure both is you can see the variation or the change between freeze-thaw conditions in the morning and in the evening. It's posted on a 3-kilometer ease grid. We post one for each day. And note, here the accuracy is that we have 80% freeze-thaw accuracy over that particular product. There are 2 level 4 products. They are modeling products. As I indicated before, they don't come as frequently as the others. This is a global product that has 2 particular collections in it. One collection provides 3-hour time averages. The other provides 3-hour instantaneous measurements. What is special about this? It assimilates the SMAP brightness temperatures out of the lower level products, puts them into a state-of-art land surface model, and using the combination of them, will come up with measurements of soil moisture at 5 centimeters below the surface, which is surface soil moisture, as well as root zone soil moisture, which is a full meter into the soil. And again, these provide data on 3-hour time averages and 3-hour instantaneous points. So there are 8 of these products, all global, every day. Notice they are completely globally covered. The model enables us to provide values over the entire Earth, not just over the swath where we're taking data with each product. You will see the entire Earth modeled on each one of these. Finally, there's the level 4 carbon product. The level 4 carbon product provides global maps of the net ecosystem exchange. Net ecosystem exchange, if you understand, if you're into this, is related to the respiration of various plants and animals. I think mostly plants, however, are talked about here, in terms of the carbon dioxide exchange into and out of the atmosphere. So we're looking at the exchange of carbon dioxide based on life respiration. If you think about it carefully, and by the way, it quantifies the net carbon flux in boreal landscapes. I should say it probably provides them anywhere where we can have it. What's important here is that freeze-thaw conditions and water conditions clearly impact plant behavior and therefore clearly impact what we call the gross primary production, which is the production of organic compounds based on the absorption of carbon dioxide. So it's the combination of the gross primary production, other measurements of respiration that lead to the measurement of the net ecosystem exchange, which again uses SMAP data, freeze-thaw data, and soil moisture data to come up with variations over the entire Earth's surface. Okay, we are it's a little towards the end here, but we're just about closing. So, where can you get more information? If you're interested in radar data, the radar data will be provided by the Alaska SAR facility DAC. This is information on how you can get to a web interface on the DAC. This is information about how you can get distribution information from them. And these are other references that they provided to me that you can use to contact people at that DAC. On to the next. The NSIDC DAC will provide all of our other data. If it isn't radar level 1, it's going to be from NSIDC. Again, they provided a website, some data search information. They indicate some of the tools that they will be able to provide. Notice they also will provide you with HDF level utilities, as well as other kinds of user support. Both of these DACs will provide you with user's guides. They will provide you with other documentation that you will need in order to be able to learn more about the individual data products. This is a sample of the NSIDC website, so this just gives you a sense of what it will look like if you go to NSIDC. This is something I want to point out to you quickly. Worldview is a means by which you will be able to view all different kinds of NASA products, including SMAP products. You will be able to look at various products, determine which ones you might want to use. You'll be able to compare them amongst themselves or with other mission products, and then you'll be able to identify them and download them. This is coming soon. This is the web URL that will enable you to be able to look and inspect at these products. And finally, last but not least, here's some information that you can use or some sources you can have to get more information about some of the topics that I discussed. As I indicated in the backup, there is even more information. So Jennifer, I'm going to hand this back to you.
Okay, thank you, Barry. We'll now move to the final set of polling questions. And what I'll do is I'll give those just a couple of minutes or so. And getting back to a point that Barry just made regarding NASA Worldview, that is a tool currently available that allows you to visualize a number of different global data products with multiple layers that you can apply. So I'll give these a couple of minutes and then we'll move to the question and answer period. All right, thanks everybody.
It's dropping.
Please mute your phones if you don't mind. Thank you. So just a reminder, if you're interested in participating in the Q&A period, which will directly follow these last 4 polling questions, be sure to stay in the room and or stay on the line. And you will also have an opportunity to download Barry's presentation on the next slide during the Q&A period. Okay, everybody. Thank you. We're going to move to the Q&A period now. Up here. All right, Barry. Before we do that, let me just make a quick note. So in the lower right-hand corner, the presentation files are available for download, and this is a persistent feature. So if you or one of your colleagues who is unable to attend would like to listen to the webinar once it's posted on the YouTube channel, you would search for NASA Earthdata, or at the tinyurl.com Earthdata webinar, which is our online Adobe Connect catalog, you would just simply highlight the file, and when you do so, when you left click, you will be presented with the opportunity to download the file. And I've posted them here both as PDF as well as in the PowerPoint format. All right. So the first question, Barry, is what is the actual depth of detection in inches or millimeters of soil moisture based on soil type, based on wetter or drier surfaces?
I think we're going to get into some questions here that I'm not going to be able to answer. So if we're getting into the specifics, what I know, and again, I'm not the scientist, I'm the data architect. So what I know is that we are advertising that we will provide 4% accuracy of soil moisture based on conditions that we have. I cannot say any details on that. Remember, this is a remote sensing situation, so that the accurate measurements are going to be based on what we see from space that are averaged based on soil, on brightness temperatures, and on radar. If we get into some other questions at this level, what I can certainly do with you is I can pinpoint other people to see if indeed some of these questions get answered. So if Jennifer asks more at this kind of level, I think what I will do is I will reference them to others so that they can provide you with answers that are accurate if they are indeed answerable. Go on from there. Sorry.
Okay, great. Thank you, Barry. Yes, so any of these questions, especially if there are questions that we don't actually get to, Barry will have the Q&A log, so we'll be able to address those offline. And feel free to email me as well, and we can, forward those questions along, both to the NASA ASF DAC or NSIDC DAC if need be. Okay, so the next question is, also, how is moisture in soil valued, volumetric as a percentage, etc., and how would one adjust for use in agriculture, which uses inches of applied water or metric suction values?
See, and again, I'll say what I know, and then again, how that would be converted would be something that, again, I would expect an agricultural scientist would know. But yes, the one point that they did come out, and they're right, is that we measure the soil moisture in volume per volume. Okay, so it's cubic meters per cubic meter. And indeed, that may have to be converted based on your particular research element to the common units that you use. And again, I am not an expert on that, but I can, and this is one thing I certainly can do, I can provide you with units, and again, I've indicated in the products, we can indicate what the units are. So again, this is something that I would not be able to do for you. I'm sorry, but again, I could reference these if you wish.
All right, thank you, Barry. And the next question is, can we get the observation azimuth angle information for each grid?
Yes.
Hey,
yes.
that's an easy one there.
I mean, if you're looking in the level 1 products, you will absolutely be able to get the azimuth measure. And by the way, when you talk about azimuth, let's be careful. You can be talking about the azimuth of a particular astronomical bodies when you're looking at the radiometer data, but also the azimuth of the antenna. You will know where that is relative to the antenna coordinate system, where 0 degrees is approximately the direction of motion of the spacecraft.
Okay, thank you, Barry. Our next question is, in addition to units, does local metadata include information on coordinate systems?
The local metadata does not contain information on the coordinate systems. Coordinate systems are referenced in the product metadata, where we indicate what the coordinate systems are used for that particular file or granule.
Okay, thanks, Barry. The next question is, what are noise levels what are the radar noise levels for level 1A, or noise levels, the radar instrument for level 1A? I think that's what you mean, Sandra.
Okay, the noise levels, there is a noise floor measure. That is something that I can find for you relatively quickly. That I don't know, but I do know that we talk about measuring above and below, above a particular noise floor. And that is available, and that's something I can pick up and pass back to you. I know the people who would be able to provide that to me.
Okay, thank you. So the next question is the observation, is the observation azimuth angle available for the level 1 radiometer brightness temperature product?
Yes.
Okay, great. The next question is, how do you account for infrastructure growth with the measurements of city sprawl, concrete, and asphalt will reflect telemetry?
The level 2 products contain or use a database, and I'm trying to recall the name of it. I believe it came out of Columbia University in New York, where they actually are looking at urban areas and urban area growth. Those particular data sets get fed into our system, and they are static for a period of time, but they certainly can be updated so that as urban areas grow or change, we can detect where they are and determine whether or not we're taking an accurate measurement or not. I hope that answered the question. At least that's what I think it was about.
Okay, thank you, Barry. If the participant needs further clarification, go ahead and type that into the Q&A pod. The next question is there any indication of RFI probability in the SMAP product?
Probability? I almost want to ask the person what they mean by RFI probability. I'm assuming what they mean is the likelihood that it would be there or not there. And if that's the case, then the answer would be no. However, what we do provide, and it goes through level 3, is we do have a bit flag that indicates whether or not RFI was detected and whether or not RFI was corrected. In other words, if we detected RFI, do we think we were successful at removing the RFI from the measurement? Now, I think most of you who are familiar with this would know that removal of RFI means removal of a few of the points involved, and in the process we might actually make the data a bit noisier, but still removal of the RFI at that particular, if we remove the RFI, we're still going to get a measurement that we can use in most cases. So we assess that. We say we detected it, we removed it, and in the process of removing it, we still have a measurement that we think is usable. The bit flags in several products will indicate that: one, detection, and two, whether or not we think the individual pixel is still usable after we removed it. And that will be on both the radiometer and the radar side, as well as in the soil moisture products. One other thing, we did actually do a 8-day cycle where we have the radar at its particular frequency detecting where we saw RFI over the globe. And again, I don't think that necessarily predicts where it will be. I don't know about that. I can tell you that at least it tells us where we see it currently now.
Okay, thanks, Barry. The next question is, how can we access the MATLAB HDF5 tool?
Okay, at the end of the particular section there, I do actually reference particular tools. If that doesn't help you get started, I can get anybody in touch with either the DAX or with people at MathWorks that can provide you with that information. It is not hard, and I know that people who have used MATLAB have been very successful at getting at those tools. So again, look at what I wrote. And when you get the presentation, look at the slides that are right after the end of what I did. Look at those first. If that doesn't help, you can either try to contact the two DACs. I think they would even be willing to help you now because they're familiar that MATLAB is so popular, or I would be able to do that as well.
Yes, and Anna or Anna, I can email you the user services, although I believe it's in Barry's presentation, information. And then another potential resource for data manipulation tools is the HDF EOS group, so I can provide that information to you by way of email. Okay. The next question is, could you review the purpose for translating SAR to RAR given resolution differences?
SAR to what?
RAR, it says. RAR?
I'm assuming that's real aperture radar. Okay. Reason for it. What I know is this, is that the SAR, let me sort of back up and say this in a more clear fashion. We take the data as a SAR. On the spacecraft, there is flight software that then merges those data into what would be a real aperture radar form. And we get both of them downloaded to us. And then we generate products for both of them. The SAR is clearly the one that we want for improving the resolution of soil moisture on the Earth. However, since we have the other data and applications can be used with those data, we provide the other as well. So one thing I want to make clear, when we talk about the low resolution data, or we talk about a low resolution interval, and we talk about PRIs, which are pulse repetition intervals, that's the frequency of each SAR measurement, and low resolution intervals, which is a combination of 48 of them, which comprises one single, shall we say, real aperture radar. That information, the telemetry is provided to us. We do the processing on the ground and provide both. One other thing I didn't mention, by the way, the low resolution radar data that we acquire is not used in subsequent processing. It's available to all of you who want to use it, but it is not used in subsequent SMAP processing, at least not now. I don't know if I answered that question either, but I hope at least I gave more information on it.
Okay, thank you, Barry. The next question is, will there be a way to download or easily subset HDF files for region of interest instead of the entire globe?
Yes. And again, this is one that I would recommend that you look to the DACs for. I know, or I'm almost certain, that one or both of them is going to use OpenDAP. I'm also aware of other applications that are coming down the pike that will enable people to online or on the cloud or whatever particular remote source that they have, be able to select subsets of the data and get what they want. And I would highly recommend people talk to the DACs about what they're planning to do and make contact with them now. I don't think that's a problem. I think they know what their plans are with both of those. That's essential because some of these products are very large, and I know you don't want all of the information. You only want a certain subset of it.
Okay, thank you, Barry. Moving on to the next question here. Okay, so this is really more of a comment, actually. There are 0 index values in the EASE2 grid column underscore ID and row underscore ID. Total range appears to be 0 to 408, but Y extent of the EASE2 grid is only 408.
Now that's something that I should reference somebody to Mary Jo Brosdick, who wrote the code or wrote the documentation of that. The EASE, I know that what happened with the EASE2 grid is they moved the center of the grid to, I think, the center of a point as opposed to the intersection between two grid cells. And I know that they did that because they discovered when they were using the original EASE grid, particularly in some areas, they were finding that the data that they were recording was not exactly what it should be. They were looking at coastlines that looked like they shadowed the real coastline. So I know that the correction is a correction so that they're more accurately representing data with the grid. Why the particular number of indices? Again, this is something that I think should go to the authors of the grid. And I do know Mary Jo back at NSIDC. She is the writer of that documentation. Again, if you wish, I could send that documentation to that person and they could then reference those people.
Sure, Barry, if you'd like to. I can also forward the comment from Alessandra to Mary Jo as well, if you like.
Okay, all right.
We can talk about that, when we're finished here. Okay,
right.
So let's see. The questions that were asked earlier, the user indicated that yes, you did answer the question for. Going back, let's see here.
Yeah, some of the folks look like they were satisfied with answers. Some may not.
Noise level, right? Okay, so let's see. Let me go back. Pardon me for just a moment, everyone, if you would. Okay, for forecasting applications, we need data very fast. How quickly can we get the data as soon as it is acquired? I guess it's more so, a latency question.
Oh, it's a latency question. I'm smiling. I've had the opportunity on this particular project, which I've really enjoyed as an engineer and not a scientist, to over the last couple of years go from one session to another where we've had potential users ask questions. And the forecasters and the modelers are two different audiences with two different sets of needs. Early on, I remember talking to people about the fact that the forecasters are going to want near real-time data, and people were saying, well, we don't have a requirement for that. Well, guess what? We're working on it now. I don't know how quickly this will come out, but I know that we're working on a near real-time product, and the near real-time data hopefully it will obviously be less accurate. We're going to have less information. We're not going to try to be as accurate, but we're working on it. I can't say exactly when it will come. So this is just an experience I've had working with NASA. Right now the plan isn't clear, but I know that we're talking about it. So I anticipate that it will happen. Forgive me if I'm wrong, but I really think that eventually it's going to take place. In the meantime, right now, yes, the latency is not really great for forecasting. I admit that, or at least not forecasting, meteorological forecasting. I would say that probably for flood forecasts and things like that, it still might be quite useful. You'll have sigma naught measurements and brightness temperature measurements within 12 hours. And I think that the 24 hours, I really bet you that most of those will come in sooner than that. You'll have soil moisture measurements well before 24 hours. So you'll be able to know if soil areas are very saturated and be able to use that kind of information. I understand the concern of that individual. I'm with them on that.
And just to add a little bit more, currently there are some near real-time data products available through our LANT system within 3 hours of acquisition, but those are more so your atmospheric data products. If you're interested, I can type the URL in here. It's earthdata.nasa.gov/LANTs, and that is where those data products would end up in the future, the SMAP data products, as we were just discussing. Okay, the next question is, are there any preliminary cost values assigned to the data level products?
Are there any preliminary, what was that? Cost?
Are there any preliminary cost values assigned to the data level products?
Are we talking about a cost to get the products? I'm not sure. Is that what this is about? Maybe the person needs to clarify.
Whitney, can you clarify if you're still on?
Because if it's cost in terms of money, there is no cost.
Right.
I'm not sure. If that's what they mean, NASA does not allow or does not charge for any of its products. If that's the interest, then I can say that is indeed the answer. If there's something else, I'm not sure what they mean by cost beyond that.
Okay. All right, so let's see. How can this mismatch be addressed when using the data? And that gets back to the question regarding the ease grid, Barry. How can this mismatch be addressed when using the data?
Are we talking about and again, I think maybe I need to actually dialogue with this person because I'm not sure what the mismatch is yet. What I can say is what we provide, and clearly whatever gridding or coordinate system we provide may not be the one that somebody else wants to use, and that means that in some situations resampling need to take place. But I'm not sure what the entire issue is here, and this might be something where either I or somebody else needs to dialogue with them to figure out exactly what this is. I'm not certain I understand it without a little more detail. I apologize.
And that actually gets back to the question regarding the total range values for the EASE2 grid, column ID and row ID, Barry. This was a follow-on. So the total range appearing to be 0 to 408 and the Y extent of the EASE2 grid only 408.
Yeah. Now, one thing I can
follow-on question, which I think maybe we can address to Mary Jo.
Okay, or one thing I certainly can do, I can look back at the products to see the gridding that I know we have on the ease grids that we have. I know that they were dictated to me. These are not things that I came up with myself, that they came up with others who were designing these products and indicated what the row and column sizes were based on the EASE2 grid where they did that work. I did not do that work. I accepted what they had. But again, we should look at this and make sure we really understand the issue and get this straightened out. This may be an issue. I don't know.
Okay. Thank you, Barry. So the next question is, are the alpha stage products available before August 1st this year?
To the general public, no. That is when we plan to distribute them in their first form. Beta, I guess, is really what they are, but still, that's when they will be distributed. You know, and I don't anticipate that it'll be any earlier than that. We do have, you will be able to, if you get onto smap.jpl.nasa.gov, one would be able to see right now some of the products that we have, and we're going to be posting more, but we don't intend to distribute them till then. And forgive us, but I think what we really want to do, and I'm sure most of the audience appreciates this, is we do want to catch some of the nubs and difficulties and issues we have and fix them. So for instance, if the previous person really does have a problem, and it really is a problem for us, those are the kinds of things that we would want to repair. If it isn't a problem for us, but it's a problem in terms of communication, we would want to make sure that we understood, that we both sides understood what was going on so that the person involved could use the product in the representation that we provide. So.
Okay, thank you, Barry. We'll take questions just for a couple of more minutes, and then at that point, if there are any, I'll leave the meeting room open for those of you interested in downloading the presentation, and further, if you have additional questions, you can feel free to enter those into the Q&A log and/or email Barry or I. If you email me, I can forward that information along to Barry. So the next question is actually a clarification to the coordinate system question, and that is, as a clarification to my question, I was asking about coordinate systems specific to the spacecraft and instrument, for example, position, attitude, not coordinate systems.
Okay, now that would be provided in documentation, and one of the things that we should do, I'm not sure if it's done, but it's something that I've been wanting to do, is make sure that that particular document or documents of that sort are referenced in our metadata so somebody could find out what they are. Yes, there are several coordinate systems that are used, and most of those should be available and known to the public so that they can figure out where these are. I can also say that the product specification documents, which will become available to people when they have them, will reference the major coordinate systems that are in use. But it gives a little more information, because if we just name a coordinate system, that's not good enough. I think this person would agree that you want more than just a name, you want a definition. Otherwise, you really don't know how to use it. And they are in the product spec documents.
Okay, thank you, Barry. The next question is the soil moisture from Radiometer better than AMSR-E soil moisture?
Thank you for asking a question like, I'm sorry, I'm not going to be able to evaluate that. Clearly, AMSR-E is a basis of where we came from. We talked about it a lot early in the mission in terms of AMSR-E demonstrated the capability to be able to use a radiometer to retrieve soil moisture. We often look at SMAS right now. I don't know how many of you are familiar with SMAS, but SMAS is a soil moisture ocean salinity mission, which is also using a radiometer and of a similar bandwidth to measure soil moisture. And we are comparing ourselves with them. And there's this third mission, which eludes my brain right now, which also we're using, and we're using validation upon them. But I can't say that we'll be better in terms of capacity. I'm expecting we will be, because we've learned a lot from them, and we certainly will be better in resolution, because that's what SMAP is all about.
Okay, thanks, Barry. The next question is, do you provide, and I'll take one more question after this, do you provide additional parameters such as runoff, evapotranspiration, and recharge in the level 4 product?
That's a Ralph Reichley question. I'm expecting that probably he can provide that information, but I don't know that it's exactly there. I actually remember evapotranspiration being discussed. I don't recall whether it's in a product or not.
So this is an example. Jesus, we will forward this referral along to somebody working on the science team, and you should be able to get an answer to that, okay?
Right. I do remember discussion of at least one of the parameters he mentioned, but whether or not that is directly in the product or not, I don't recall.
Okay. All right, wonderful. Thank you, Barry. Let's see. Well, there is an answer here. The level 1C SO high res will have 4 polarizations, HH, HV, VH, and VV. Or is this a question? I guess this is a question from John Ranson, Barry. The level 1 CSO high res will have 4 polarizations, HH, HV, VH, and VV.
All right, I'm glad they mentioned that, because that was in the slides, and I didn't, as I was trying to forge through, I didn't get it clear. So let's back up a moment. With the 1C and the 1B. In the 1B, yes, you will have HH, HV, VH, and VV. And by the way, our standard when we're listing the 2 polarizations is the second polarization is the transmit, the first polarization is the receiver. So when I say HV, I'm saying V transmit, H receive. I trust that you understand it the same way. However, in the L1C, we are only going to provide one copole channel. So we're going to have HH and VV, but then one of the two will get selected, and we have an ability to select one or the other. And I'm trying to pull on my brain. I do think that right now the selection was HV. I could be wrong. But again, that's something that we select, and we selected one, or we're planning to select one over the other based on the quality of the data and also the frequency of RFI. We would like to pick one that would have less RFI contamination, but it's only one of the two in the level 1C.
Okay, that was our final question for this webinar. I'd like to take a moment to thank all of you for participating today. If there are any further questions, please feel free to enter those into the Q&A pod, and I will be sure that those questions get addressed. And as mentioned earlier, all of the questions have been captured in this log, and for some of the participants, Barry will be able to follow up offline with each of you to ensure that your questions have been answered. Okay, so thanks very much, everybody. At this point, we will log off from the telecon, so you will not hear audio any longer. However, I will leave the room open for 10 minutes. All right, thanks, everybody. All right, bye-bye.